So we're still talking about electrical circuits, about the hardware side of these IoT devices. Now, we understand V equals IR, Ohm's law, and so forth, that relationship. But you're eventually going to have to actually build these things physically. You're going to have to take these components. So we saw, a battery, some kind of power source, wires, resistor. There are lots of different components. Eventually, you're going to have to take these and actually plug them together and make a circuit out of them. Okay. Now, typically, when you do that, you also have what's called a schematic diagram, and we're going to show some of these. But so you start off usually when, say, you're thinking of a new design. What you do is you draw out a schematic, a drawing of what should be connected to what. Now, this schematic drawing, typically, it shows what components connected to what terminals connect to what, but it doesn't show exact placement. It doesn't show how it will physically look in the real world. It shows, though, how you expect it to be connected electrically. Okay? So these schematics, we're going to have to get used to reading these schematics. And given a schematic, you're going to have to get used to taking that schematic and implementing it, meaning wiring some components together according to the schematic. Okay? So that's the type of stuff we're going to cover right now. And so we're going to go through some of these electrical components that you commonly see, just so you know what they look like and what their schematic symbols look like. So that you can understand what a schematic diagram looks like, and then you can understand how that matches the actual physical implementation that you're going to work on. So up here we have resistors. So on the left you see a batch of resistors. So those are resistors. Those are your standard resistors. And they can look different, but that is a common look. So if you look at those resistors, and you can see next to it there's a schematic symbol, that little sawtooth type of diagram, the sawtooth thing. That's a resistor's schematic symbol. Now a resistor, it provides resistance to the current flow. So we already talked about what a resistor is supposed to do. A resistor has two terminals, two leads, right? Two wires coming out of it. If you look at any one of those resistors, there's two wires, one on each side. And it doesn't matter which one, they're equivalent. So current can flow either direction through there. It doesn't matter which one is which side is which. Now, each resistor has a certain resistance value associated with it. Maybe this resistor is 10 ohms, maybe this is 10K ohms, meaning 10 kilo ohms. Maybe this is 100 ohms, and so on. So every resistor has a resistance, and that resistance is encoded in the bands on the resistor. Now, I'm not actually going to go through the band coloring, but let me tell you how it basically works. These resistors generally have either 4 bands or 5 bands of different colors. I think the ones on the screen, hard for me to see at this distance, but they have 4, maybe it's 4. 4 or 5. So one of the bands is at one end is always the accuracy of the resistor value. So whenever you say I got a resistor and I say, it's a 100 ohm resistor, it might not actually be exactly 100 ohms. That's plus or minus 5% or plus or minus 10% or something like that. So that plus or minus percent, that's represented in the last band. So typically, resistors that we have, they have a gold band as the last band, which means pretty good. I forget what that means. Maybe I think that's 5% plus or minus. And then silver, I think, is 10%, something like that. So there's one band at one end that is how accurate the value is on the resistor. The other bands, each band represents a digit. So if you were to Google resistor color codes, you would see these tables where they show black is, I believe black is like a 0 or something, and brown is a 1. Right? Every color is a digit. And these bands, so say you've got a 4-band resistor, right? One band is the accuracy, but the other 3 bands, they represent 3 digits. And it's basically scientific notation. So the first 2 digits are just 2 digits of the number. Let's say it's a 2 and a 2. So 2, 2. And then the last digit is the exponent of 10. So let's say I had 2, 2, 3. That would mean 22 times 10 to the third. That's how many ohms resistance the resistor is. So that's how you read them. So you need to have the color code sheet in front of you. It's sort of a tedious thing. And you can read the colors off the bands and figure out the size of your resistor. It's tedious also because the coloring, how good is your estimation of coloring? Meaning they'll have shades of colors that look kind of similar. Like the orange sometimes looks like the red, things like this. It is awkward to read these bands. But that's what you have to do. So now what I actually do, tell you the truth, I have tons of resistors. I basically, when I get them, they come in a bag that says what resistance they are. I just keep them in that bag. Okay, so I never have to read the bands again. But you can always resort to reading the bands if you have to. So just Google it and you can find the color codes, and that's that. So those are resistors, and that's their schematic symbol. Okay, here are some more schematic symbols for some common components that you get. First, we got the battery. Now, notice the battery has basically it's a long bar and a short bar. The long bar is the positive terminal. The short bar is the negative terminal. Now, sometimes you're driving something with a battery, but sometimes you're driving it without a battery. You just have a power source, maybe from the wall or some arbitrary power source. So, for instance, actually in our examples, all of our examples, we're not using a battery. We're using the Arduino itself, right? The Arduino, we're going to pull 5 volts and ground from the Arduino itself. So we won't use a battery. Instead, we'll just have a power symbol and a ground symbol on our diagram. So power is actually drawn several different ways, but we're going to use this a little triangle that points up like that. That's usually power, and next to it you would have the power, the voltage value. So for instance, if it was a 5-volt source, you'd say power, you'd have the little triangle, and next to it you'd write 5V, plus 5V, something like that. Now ground is actually almost always drawn exactly like that. Ground is just, it goes down and it's those 3 bars, smaller one after the other. So those are some common symbols. You see those in schematics all the time. DC power, so this is all direct current, DC. Just to note this, we're dealing only with direct current. So to tell you what direct current is, there's direct current versus alternating current. Alternating current is when current goes back and forth. The electrons can move back and forth. Like coming out of the wall, I believe we got 60 hertz. I think it's 60 hertz coming out of the wall, which means 60 cycles a second. So the current goes back and forth 60 times every second. That's alternating current. Alternating current is good for transmission, meaning it loses less power in long-distance transmission. Okay? That's why we have alternating current in our houses and things like that, because you got to transmit it from wherever the power station is, and it transmits better. But direct current is what we use in our devices in our houses. So there's always this conversion from AC to DC. Direct current into our devices, like a TV or something like that. That runs off of DC. So all of our circuit boards, our Arduinos, all that junk, that runs off of DC. So one other note, never create a short circuit. So a short circuit, actually specifically a short circuit between power and ground. Short circuit is when you accidentally connect 2 wires together. Now if you were to short power to ground, so if you took power and ground and wired them together by accident, then then what happens is between those 2 points, you've got, let's say power is 5 volts, okay? So you got a 5-volt difference between ground and power. But the resistance is 0. If you have a conductor, if you run a wire, you got effectively no resistance. Now, if we were to go back to Ohm's law, V equals IR, right? So I, the current, equals V over R, V divided by R. If R is close to 0, then I is infinite, or approaching infinity, right? So what that means is if you short power and ground, you get a rush of current, and something smokes, literally smokes. I mean, you'll see something on your board, smoke coming out, you'll smell it, it'll be extremely hot. It's not overly dangerous because we're dealing with low current levels, right? But you don't want to do that. And you can mess up your breadboard too. It'll brown out a hole and might hurt it in the future. So you don't want to do that. So never short, put a short between power and ground.